So this is the second lecture on Green's theorem, and in the last lecture, what we did was we established Green's theorem. We actually provided a proof for it, which is this statement over here. So let me just quickly recap that. So what you have is you're in R2, and you have some sort of region like this region, which is denoted by R over here, which is in R2, and we denote by dr the boundary of the region, right? So in this case, it's going to be a curve. Clearly a curve. It's going to be a closed curve which encloses the region R. And in that case, what Green's theorem does is it establishes a relationship between a certain type of double integral over the region R. So this dx dy is an integration with respect to dA, d capital A, which is the area element, and a line integral where you're doing a line integral around the boundary of the region. So you're doing the line integral along the curve, the closed loop, which encloses the region R, and that denotes the fact that this is a closed loop. And this is so for any functions u and v. So u and v are both functions in R2, so functions of x and y each, and they need to be in of class C1. That means that the first derivative has to be continuous. So continuous the differentiable functions u and v, and if so, we have this statement over here. And in the previous lecture, what we discovered was that we could extend this to regions R which were more complicated than this one over here. It could be regions where R comprised two different disconnected regions, or it's something which is not simply connected, something which has a hole in it, and so on and so forth. But anyway, so this is Green's theorem, and what I want to do in today's lecture, this second lecture, is I just want to do several examples related to Green's theorem. So let's do this example first, and this is a fairly classical example related to this. So there's a little error here. Okay, that's minus sign. And so let's see be a simple closed curve enclosing a region A, which is a subset of R. So here's the picture that we're talking about. So we've got a simple closed curve. So simple means that it's non-intersecting, so you can't have a figure 8 type type curve. It's non-self-intersecting, and it has to be closed, of course, because if not, it's not going to enclose a region. It has to connect back onto itself. So C is the boundary of the region A. Okay, and what you're asked to show is that the area of this region A, so the actual area of this region, can be represented in terms of a particular line integral, and the line integral over the outside, the boundary of A. And this is this seems like a pretty interesting result, in the sense that what you're trying to do is you're trying to figure out an area here, and what this is telling us is that we don't really need to figure it out as an area. We can actually figure it out by doing a line integral around it, which is kind of amazing. So let's see. So let's try to establish something that we know. Well, the area of A, I know that the area of A, I can write it in this way. It's going to be a double integral over the area element, right? So the area element is d capital A, which I can write in terms of dx dy or dy dx. It's exactly the same thing. And then I just need to add these together, right? So I have these little elements like this, and I need to add these together. So the area of A I can express in terms of a double integral. But what's given here is a line integral. So clearly, what we need to do is we need to establish a connection between this double integral and this line integral, and Green's theorem provides us exactly with that. So let me write down Green's theorem down here, the conclusion of Green's theorem. So in this case, A is my area, and C is the curve which bounds that area. Okay, and this is true for any functions u and v. Now, what I'm going to do is I'm going to go back and look at what's given to me here. I'm going to start with that, and hopefully I'm going to establish a connection with that. Okay, so I'm just going to start with this right-hand side. So when I write down the right-hand side, well, there it is. And then what I need to do is I'm going to apply Green's theorem clearly, and then I need to figure out what is the relationship between Green's theorem and this. So if I look at this statement here, here is my line integral, and that has to be equal to the line integral over here. So then I just need to identify functions u and v. So I'm going to define a function u to be the function negative y, and the reason for that is because then this is going to be u dx. This term over here is going to be u dx, which is that term over there. And then I'm going to define the function v of xy to be the function just x, and then that term becomes that v dy, right? So the first step is to introduce these functions, right? So I define these functions, and once I define these functions, then I can just go ahead and apply Green's theorem. So let me go ahead and do that. So first I got the half. I'm just going to write that down as it is. And Green's theorem tells me that this line integral has to equal that. So what I need to do is I need to figure out this quantity over here, right? The derivative of v with respect to x minus the derivative of u with respect to y. So this is easy enough to do. So the derivative of derivative of v with respect to x, that's my first term, but v is equal to x. Yeah, so that's that. So this becomes that. So it's the derivative of the function x with respect to x. Then I have my minus sign. And then what I need over here is the derivative of u with respect to y. And u is the function negative y. So I put the negative y over there. Okay. So that's clear. So this is a direct, straightforward application of Green's theorem. And of course, the standard conditions are met because these functions are infinitely differentiable, right? So they only need to be of class C1 in this case. Okay, now let me just go ahead and do these derivatives. These derivatives are trivial. The derivative of x with respect to x is just 1, and the derivative of negative y with respect to y is negative 1. So I can actually fill out the next steps very, very quickly. So I'm going to get a 1 from here, and I'm going to get a negative 1 from here. Then I have 1 minus negative 1, which is just 2, and that 2 is going to cancel with that 2, so I'm just left with this. Yeah, so I started off with this expression, and I'm just left with that, which I know is the area of A. So I'm done. So the Green's theorem gives us this almost instantaneously, which is a really, really nice result. Now, why is this result interesting? Well, it turns out that this result has been used in applications from the 1800s onwards. And the application that's being used is something which is called a planimeter. So this is something which is used by surveyors, and it's this object over here that you see. So this point, it traces out a region. So for example, if you want to find an area of a region like this, you set up your planimeter, and then this point will trace out the various points on the boundary of the area. And when it's doing that, right, so this first point will be x1 y1, second point will be x2 y2, which you assume is quite close to x1 y1, and so on and so forth. So you go along the region, all the way around the region until you come back to the beginning. The beauty of this instrument is that it actually records the x, y locations and so on. So if you go from x1, y1 to the next point, x2, y2, well, you know the x values at each of these points, but you also know the change in x and the change in y. So now remember that what we established was that this was true. So we can approximate this. Now remember, an integral is just like a summation. So x dy, at any one of these locations, it's xi times the change in y at that location. So you're going from here to here. So it could be x2 times the change in the y coordinate as you went there, and similarly over here, and then you just add all of these things together because the summation is going to approximate your integral. So this planimeter, is a device which automatically does all of these calculations, and it tells you then. It does this calculation, and therefore it just calculates the area of irregularly shaped objects. So this is pretty neat. And this picture that I have over here is from the US National Archives, showing some surveyors using the planimeter. So here's an example in which you have this sort of theoretical you have this theorem, the Green's theorem, which seems like a purely theoretical object, but it has a very genuine application. And then, of course, there are many other applications like this of mathematics that people develop, potentially purely for theoretical reasons, but still they do have many applications. Okay, so let me just point out that Green's theorem can be used to convert a closed line integral into a double integral over its interior. Right, so that's one of the things that Green's theorem does. So another possible usage of this is that you can convert one of these integrals to the other. Right? If you're trying to do, say, this closed line integral, and it's difficult. Now remember, there are certain ways in which you do line integrals. You have to do parametrization of the line, and so on and so forth. And you find it difficult. It might be easier if you look at the equivalent double integral. Right, so in a double integral, you don't necessarily need a parametrization in that sense, but you need to be able to write it as an iterated integral, or vice versa. So sometimes this might be quite difficult, but it might be easier to do it with the closed line integral. So it's not always clear which is easier, but sometimes one or the other is easier, and therefore Green's theorem gives you an additional tool to help you do certain types of integrals. Okay, but more importantly than that, at least to my mind, is that it's a very fundamental theoretical tool. Right, so it turns out that when you go and study complex analysis, for example, Green's theorem becomes a really important tool, which helps you give some fairly powerful results in complex analysis as well. And then it's got all of these neat applications, like, for example, this application over here, which just sort of emerges by usage of the theorem, right? So it's a pretty neat theorem. So let's do another example, just to illustrate how this works. So in this example, we are asked to find the circulation of a certain vector field. So the vector field is given to us. It's this thing over here, x over 1 plus y squared is the x component, and the inverse tangent or the arctangent of y is a y component of this, right? And you're asked to find the circulation of this around the unit circle. Now the definition of the circulation is this integral over here. So it's just a work type integral, but it's called a circulation because you're actually going all the way around a curve, right? So in this case, you're going all the way around the unit circle. And when you're doing this f dot dr, you're looking at the projection of f in the direction tangential to the curve. So if f is in that direction, you look at a projection tangential to the curve. So it's something like that, something like that, something like that. So adding together the components of f along the curve, if you will, and therefore it's telling you something about the rotation, the rotational impact of f, which is why it's called the circulation. Anyway, so we're supposed to find this around the unit circle. Now, what does this mean? Well, we know that dr in general, we are just in R2, so it's got two components, dx and dy are the two components. So when you take f dot dr, what you need to do is you need to take the dot product of this with the vector dxi plus dyj. And that's what you need to do, and that's easy enough to write down. So you get this times dx, that's that term over there, and then you get this times dy, and then you have to add these together. So here's the integral that you have to do. Okay, now when you're doing this integral, we have to be careful here. So you can try to split this into two integrals. This one, for example, is one, and that's going to be the other one. But when you're doing this integral, it's with respect to x, and you have to then write everything with respect to x. And the fact is that y is actually changing as you change x as well, right? As you go to new locations, both x and y are changing. So you kind of need to know what y is as a function of x, and then it just becomes a bit of a disaster. So that's hard to do. So the standard approach for dealing with integrals of this form is to parameterize, and the unit circle is of course easily parameterized by just having x equals cosine of theta and y equals sine of theta, right? So it's just by using the standard polar coordinate parameterization, and then you can write everything in terms of theta and have a go at doing this. But it turns out that this is actually quite difficult because y is sine theta, right? So what you get here is inverse tangent of sine theta, and then you're going to get something for the dy as well. Not so easy, and you're going to get some complication over here as well. So it turns out this is not really easy to do. Okay, so let's try another approach. So this is a line integral, and in this section we're talking about Green's theorem. So let's convert this using Green's theorem into a different type of integral. An integral, rather than doing an integral around this loop, we're going to be doing an integral on the interior of the circle, right? So what I've done here is I've written down Green's theorem so that we have that as a reference. And here's what we had from the previous slide, right? So if I'm trying to use Green's theorem here, what I do is I look at this and I say, look, this is going to be equal to that. So therefore, I have to make an identification as to what my function u is and what my function v is. So clearly, what I need to do is I need to take u equals this function over here, x over 1 plus y squared. And then v has to be equal to the inverse tangent function of y, right? So in general, u and v are both functions of x and y. Okay, so now I made that identification. So then I can go ahead and apply Green's theorem. So Green's theorem tells me that this side is equal to this side. So I need to do this calculation here. So I need to do the integral over the interior. So r is going to be the interior of the unit circle of these derivatives, right? dv by dx minus du by dy. Now dv by dx, so here's my v as a function of x and y. When I take the derivative of this with respect to x, there's no x there, so I just get a 0. So that's easy enough. And then I need to subtract from that the derivative of u with respect to y. So here's my u with respect to y. So rather than being silly and trying to use the quotient rule here, I realized that I can write u as x times 1 plus y squared to the negative 1. And this is much easier to differentiate with respect to y. So when I differentiate this with respect to y, what I get is x stays in front. Yeah, I treat it like a constant. Then I get negative 1 times 1 plus y squared to the negative 2. And then by the chain rule, I'm going to have to put a 2y there as well. Okay, so that's what I get, and then I have dx dy. Okay, so here's me applying this here, and I noticed some nice things. That's this first term is a 0, and then there's 2 negative signs, so those are going to cancel. So what I actually get is this integral here. So here's the integral that I need to do. It's that integral, and if I rewrite that with this negative 2 in place, what I need to do is this integral. So it's not clear to me that I've actually made my life easier, and possibly I've made my life more difficult as well. But what I'm going to do is I'm going to see whether I can evaluate this integral. Okay, so what I need to do now is I'm going to do a double integral. Of course, we need to write it as an iterated integral. So there's several ways in which you can do that. But in this case, what I'm going to do is I'm going to choose my x to be my outer integral and y to be my inner integral. So x is my outer integral. So my limits go from -1 to 1, as is obvious over here, right? So x is -1 on this side and x is equal to 1 on that side. And then my y limits, how do I find my y limits? Well, I take a general x location, and along that x location, I figure out what happens to my y limits. So the lower part of the circle is y equals negative square root of 1 minus x squared, and the upper part is y equals positive. So I just write this down: negative square root 1 minus x squared and positive 1 minus x squared. So I'm beginning to get a little worried here because it looks like this is going to be actually quite difficult. Okay, and then what do I do? So I have the function that I'm trying to integrate. So before I write down this function here, so I got this function here. Before I write down this function, let me write down this quantity out here as well. So I'm writing that as dy dx. Notice that, over here I've written it as dx dy, but here I've now gone to dy dx because I'm choosing x to be my outer integral and y to be my inner integral, right? So just because of the way in which I've chosen to do the calculation over here. Okay, so now I have this function in here, which I'm going to put in there, but then my y is my inner integral. And while I'm doing my inner integral, I remember I work my way outwards, sort of thinking of these as nested brackets. When I do my inner integral, I essentially treat x like a constant. So that enables me to actually pull out the x. So this x that I see here, I'm going to pull out, and then I'm left with the function 2y over 1 plus y squared. Okay. All right. Now this looks pretty difficult, right? And it actually is. It would be a little bit difficult to try to do this, but let's see. Let me look at this integral first, the inner integral. Remember, I said that you kind of try to treat this as if they're nested brackets, and you work your way outwards. So if I look at this in integral, I'm integrating with respect to y. Because of what I see over here. So integrating with respect to y, and I can see that this is over a symmetric interval, right? Negative some value to positive some value. So I'm integrating over a nice symmetric interval, symmetric around y equals 0. Right, so that's what I'm trying to do here. Okay, so that's a nice observation. So it's a symmetric interval. But let me look at the integrand that I have here. The integrand actually is an odd integrand. This thing is an even integrand. This part is even because I've got a y squared, and then I'm squaring that again. So if I replace y with negative y, it remains the same. But on the other hand, here, if I replace y with negative y, I'm going to get negative what I started with. So this entire integrand is an odd. It's odd with respect to y equals 0. Yeah. So whatever contribution I get from y positive, I'm going to get negative that contribution from y negative. I'm integrating this over a symmetric interval. So that's very easy. That tells me then that my integral. So I got that x dx over here, but the integral that I just did, this inner integral, is going to give me a 0 because it's an odd integrand, and then I'm done, right? So this whole answer is 0. So my answer is 0 in this case. The circulation of this vector field, around the unit circle is 0. Yeah, which is pretty neat. well, it's easy to it's been relatively easy to calculate this, and using Green's theorem. Okay, so that's another example of the usage of Green's theorem, and that's it for this section.